In this lesson, we will focus on Task 3.3, Case 2. Within Project 3, Composite Processing Technology and Advanced Manufacturing Case Analysis, specifically exploring the application of special processing techniques for microstructures and molds. We will delve into the concepts and characteristics of special processing technologies, understand common special processing methods and their applications in microstructure and mold manufacturing. Through cutting-edge manufacturing cases in national strategic industries such as aerospace engines and micro-electromechanical systems, we will appreciate the importance of multi-technology integration and inspire a sense of mission to serve the major strategic needs of the nation. In today's rapidly evolving manufacturing industry, composite processing technology is becoming increasingly important, and special processing plays a crucial role in the field of microstructure and mold manufacturing. Special processing refers to the direct use of electrical energy, thermal energy, acoustic energy, light energy, chemical energy, and electrochemical energy, sometimes combined with mechanical energy, to process workpieces. Compared to traditional metal cutting processes, special processing offers many unique advantages. Traditional processing primarily relies on mechanical energy, removing material through the relative motion between the tool and the workpiece. In contrast, special processing is not limited by the mechanical properties of materials such as hardness and strength, allowing for the machining of various high hardness, high strength, and high toughness materials, such as hard alloys and titanium alloys. The characteristics of special processing are also reflected in machining precision and surface quality. It can achieve small-scale machining, enabling the production of microstructures and molds with complex shapes and high-precision requirements. For instance, in the manufacturing of electronic chips, where microstructures at the micron or even nanometer level are needed, special processing technology can meet such high-precision demands. Electrical discharge machining. Electrical discharge machining is a method of processing materials using the electroerosion phenomenon generated during pulsed spark discharge between the tool electrode and the workpiece. Electrode. The basic principle involves applying a pulsed voltage between the tool electrode and the workpiece electrode in an insulating working fluid. When the distance between the electrodes is reduced to a certain extent, the working fluid breaks down, forming a discharge channel and generating instantaneous high temperatures, causing the workpiece material to melt and vaporize and subsequently be eroded away. Electrical discharge machining is suitable for processing various conductive materials, especially difficult to cut materials such as hardened steel and hard alloys. In mold manufacturing, EDM is often used to process mold cavities with complex shapes, such as plastic molds and die casting molds. For example, when manufacturing die casting molds for automobile engines, the complex shape of the mold cavity makes it difficult to process using traditional methods. However, EDM can precisely machine the shape of the mold cavity by creating suitable electrodes. Laser processing is a method of material removal, joining, and modification using a high energy density laser beam. Lasers are characterized by high brightness, high directionality, high monochromaticity, and high coherence, allowing them to be focused into extremely small spots and generate extremely high energy density. Laser processing can be used for various machining processes such as cutting, drilling, welding, and surface treatment. In microstructure manufacturing, laser processing has unique advantages. For example, in the manufacturing of microelectromechanical systems, lasers can be used to process microchannels, microsensors, and other microstructures. MEMS are miniature devices or systems that integrate microsensors, actuators, signal processing and control circuits, interface circuits, communication, and power supply. They are widely used in fields such as aerospace, biomedical, and automotive industries. Laser processing enables high-precision, non-contact machining, avoiding the mechanical stress and damage that may be caused by traditional processing methods. Electrochemical machining is a method of metal removal that utilizes the principle of electrochemical anodic dissolution. It includes processes such as electrolytic machining and electrochemical polishing. In electrolytic machining, the workpiece is connected to the anode and to the cathode within an electrolyte solution. A direct current voltage is applied between the electrodes, causing the metal on the surface of the workpiece to undergo anodic dissolution under the influence of the electric field, thereby achieving material removal. Electrochemical machining is suitable for processing various high-hardness, high-strength conductive materials and can produce complex profiles and cavities. In the manufacturing of aircraft engine blades, where the blade shapes are complex and the precision requirements are high, electrochemical machining can ensure the machining precision and the surface quality of the blades. Aircraft engines are the heart of airplanes, and their manufacturing technology is a significant reflection of a nation's technological prowess and comprehensive national strength. Electrochemical machining technology plays an important role in the manufacturing of aircraft engines. Aircraft engine manufacturing. The manufacturing of aircraft engines involves many complex microstructures and molds. For instance, the turbine blades of aircraft engines have numerous small cooling channels on their surfaces, and the machining precision and surface quality of these channels directly affect the engine's performance and reliability. By employing special processing techniques such as electrical discharge, machining, EDM, and laser processing, these small cooling channels can be precisely machined. Additionally, when manufacturing molds for turbine blades, special processing can also meet the requirements for complex shapes and high precision. The manufacturing of aircraft engines requires the integration of multiple technologies with precise control needed at every stage, from material selection and process formulation to quality inspection. This necessitates mastering system integration capabilities, combining various special processing techniques with other manufacturing technologies to produce high-performance aircraft engines, thereby providing strong support for the development of our nation's aviation industry. Micro-electromechanical systems. MICE are miniature devices or systems that integrate various functions such as microsensors, actuators, and signal processing and control circuits. In MEMS manufacturing, special processing techniques are crucial. For instance, photolithography and etching techniques can be used to create micron-scale microstructures, while laser processing and electrochemical machining can further process and modify these microstructures. Microelectromechanical systems may have wide applications in fields such as biomedical, environmental monitoring, and consumer electronics. For example, in the biomedical field, MEMS can be used to manufacture miniature medical devices like microsensors and microsyringes. These devices enable real-time monitoring of physiological parameters and precise treatment. In the application of special processing for microstructures and molds, a single special processing technique often falls short of meeting complex manufacturing demands, making the integration of multiple technologies particularly important. For instance, when manufacturing molds with complex shapes and high precision requirements, electrical discharge machining, EDM, can be used for rough machining to remove most of the material, followed by laser processing for fine machining to enhance the surface quality and the precision of the mold. The integration of multiple technologies not only enhances processing efficiency and quality, but also expands the possibilities of processing. In national strategic industries such as aircraft engines and microelectromechanical systems, the integration of multiple technologies is crucial for driving industry development. As future professionals in the manufacturing industry, we must recognize the critical importance of mastering system integration capabilities for building a strong manufacturing nation. We should strive to learn and master various special processing techniques and related manufacturing technologies to contribute to the development of our country's manufacturing industry. In the development of national strategic industries such as aircraft engines and microelectromechanical systems, our country faces numerous challenges and opportunities. The application of special processing techniques in these industries reflects the spirit of continuous pursuit of technological innovation and breakthroughs in our manufacturing sector. As university students in the new era, we bear the mission of advancing our nation through technology. By studying the application of special processing for microstructures and molds, we must deeply understand the importance of integrating multiple technologies. We should strive to enhance our system integration capabilities and actively participate in the development of major national strategic industries, contributing our wisdom and strength to the transformation of our country from a manufacturing giant to a manufacturing powerhouse. In this lesson, we focused on the application of special processing for microstructures and molds in Project 3. We first explored the concept and the characteristics of special processing techniques, which offer unique advantages compared to traditional processing methods. We then introduced common special processing methods, including electrical discharge machining, laser processing, and electrochemical machining, as well as their applications in the manufacturing of microstructures and molds. Through case studies in national strategic industries, such as aircraft engines and micro-electromechanical systems, we gained a deep understanding of the importance of integrating multiple technologies. Finally, we emphasize the responsibility of system integration and the mission of advancing our nation through technology. I hope everyone can remember their mission, strive to learn, and contribute to the development of our country's manufacturing industry.